Right, so thank you very much for the organizers to give me the opportunity to be here talking to you. I'm Samuel Mañas. I'm working in the group of Tuno van der Sar. Indeed, I guess you were waiting for him. Unfortunately, he couldn't do it. But what I can tell you is that about the details about this talk, I can tell you much better than maybe him, right? Because I was doing them. So as the chairman mentioned, we're going to be talking about imaging and control spin waves with spin in diamonds, so MV centers. But somehow I like to more call it like this, like magnons at the beach. And somehow this is the summary of the talk of today. So we're going to be having spin waves. We're going to be making an imaging using a single spinning diamond. And the way that we're going to be dealing with the beach is because we're going to be studying a magnetic film, very simple one, permalloy. And in particular, we're going to be measuring in the edge. So somehow when the magnetic film finishes and then we start in the silicon substrate, similar as you may have in a beach, right? So the ocean and the waves finishing, just because here you have the land. All right, so let's start from the beginning. What is this kind of a magnon of a spin wave? Well, it's rather simple. It's simply a collective excitation of the spin. Here you can see what is known as the ferromagnetic resonance. So all the spins are, precessing in phase. However, we can have another kind of spin waves, for example, as this way in the bottom, where you can clearly see that we are having spins that are precessing, but not in phase. And somehow with that, we can define, if you want, a wavelength. So in this case, we will have a wavelength of 9 spin, talking in that kind of way. And why are we interested in the study of magnons? Well, this is just something similar as well, the deal of magnon spintronic, that at the end is try to replace electrical currents that, they can dissipate and have a Joule effect by these kind of oscillations, by these magnons, and then somehow, eventually, we could use it for transferring information. However, there's really a big challenge, I guess, in any of these kind of fields. It's just how you can try to miniaturize this kind of phenomena, and in particular, make it like kind of, if you want, CMOS compatible, because if you have a magnetic field in bulk is one thing, but in the moment that you're trying to go to the nanoscale, reduce dimensions, add in edges, so you have magnetic inhomogeneities that at the end are going to be influence your spin wave propagation. So in this case, ideally, for example, we could be using a van der Waals magnet, as we already hear in case of chromium sulfur bromine, chromium PS4, and somehow the dream, and this is just general for any device, right? So you have something that you want to transfer, in this case, will be information in somehow encoded in the phase of this spin wave. We need to generate it, we need to detect it, and finally we need somehow to control it. So somehow this is just what we're going to be doing in the next slides with a very simple, very simplified magnetic device. And this is what I like to call my beach. So we have simply a silicon substrate. Here we're going to have a top layer of permalloy, and we're going to be here adding a gold strip line. And we're going to be imaging just here into the gap. So just be aware that it's not on top, it's just next to it, and we're going to be having a gap. So somehow this is just like the real sample we're going to be measuring, something very simple, simply a rectangular of permalloy with a strip line next to that. So somehow this is just this mimicking of being at the beach. How are we going to be measuring? So, well, first of all, we need to apply some kind of music. So that's the thing that we're talking about generally, right? So we're going to be doing it just by applying here a frequency at 2.87 gigahertz. So that's the frequency we're going to be working in all the images that we'll be showing you today. Then we need to control these spin waves. We're going to go to the very simple case. It's just simply applying a magnetic field. Just, changing the magnetization of the film, and that will be our first approach. And finally, we need to detect these spin waves, and this is just when the single spinning diamond enters into place. Well, let me talk a bit about this diamond and the properties. So what is a spinning diamond? So indeed, it's a defect in the carbon lattice that somehow we can just, well, it behaves as a paramagnetic spin of spin equal 1, and this is just the thing that we're going to be taking into approach. And the particular interest of that is that we can read it optically, because all the measurements are going to be like that. So basically, we have spin 1, two-level systems. We have ms equals 0, ms equal plus minus 1. We're going to be exciting with a green light. And if we are, let's say, the tune, so we're going to be coming to the ms equals 0. So we're going to be reading the PL. We're going to have, let's say, high PL. But in the moment, let's say here by applying a frequency, we're able to go to ms equal plus minus 1, we're going to be having less photoluminescence. So this is the kind of dip that we're going to be measuring. And from this kind of measurements, you can get, as you can see, two values. The value where we're going to have in this dip of the electronic spin resonance, the ESR, and the contrast. And the contrast is important because it's given, let's say, by the power that the single spin defect is filling. And it's just be two main sources of contribution in our case. So first of all, the external microwave that we're applying, so that's one. But then the second one, it's going to be the spin wave. And since this stray field produced by the spin wave is going to be changing in space, that's what we're going to be sensing, and by tracking the contrast, somehow we can indirectly measure what is going on. Well, the basis of magnetometry then, in the moment that you have this kind of a defect at a frequency given by the zero field splitting, is as you apply a magnetic field, you have a Simon splitting, and if you are able to measure these two dips, you know the magnetic field, and this is somehow what is used for doing this kind of a quantum sensing. Typically, for example, for seeing 2D magnets is very useful, but in particular today, are we trying to focus on detecting spin waves. All right, however, there's a problem, right? Because we're going to be applying a magnetic field, and as I told you, if we apply a magnetic field, we have a splitting of the zero field, like just following the Thiemann term. So that means that the spin waves that we can measure are not at the same frequency anymore. So somehow the trick that we're going to be applying today is just we're going to be using a single spin, and then we can orient it, and we're going to be having it an out of plane and be centered, or magnetization is going to be in plane. So then what you can see here is that at first order we can decouple the magnetic field sensed by the MV center with the one that we use for Taylor demagnetization. So somehow we're able to measure in an isofrequency way spin waves below the ferromagnetic resonance. So in this part here. So how is just the setup that we're having is just very simple. We are going to be having a confocal microscope, and well, here you can see the objective. And here, yes, in the bottom, what we're going to be placing is a single spin sensor. So this is mounted in a tuning fork. Indeed, this is commercially available. It's from QSaver. And then in the other part, we're going to be placing here is just simply the sample. And the sample, we're going to be using it for scanning as in a conventional AFM. And in this case, in this part, we're going to be putting our magnetic beach. All right, so let's going to go to the results. So that's how it looks like, our contrast maps. So we're going to be scanning our sample. So then with the tip, we're going to be scanning all over the sample. And just let me dive you a bit what we are seeing here. So first of all, here we have just the bare silicon. So we see no contrast at all. Here we have the strip line that, as you may be expecting, is just the high intensity signal because just simply we're driving our MV center strongly. And then here we enter into the ocean, we enter into the permalloy film. And clearly you can see some oscillations of the contrast that we're measuring just by sweeping on and off the microwave. And here in the top panels, what you can clearly see is the waves, because this is just coming from the 1D average of all this 2D plot. So once we are doing this with one magnetic field, what we're going to be doing is very simple. Just we're going to be rotating the magnetic field in plane, and this is what you can see. So clearly you can see how we're going to having different spin waves, and just by the naked eye, you can see just that the wavelength is changing, right? And somehow this is something of the powerful technique that I like. It's just that you don't really need to be an expert to see that you are having spin waves or what is going on. That's something I could show to my grandmother, and she just can clearly see that here you have some oscillations and you have some patterns. Well, this is just the picture how we can tune and control them. Let's gonna just go a bit into detail in some particular cases. So we can go to the case that the magnetization or the external magnetic field is applied perpendicular to the strip line. So let's say pointing to the right, pointing to the left. In both cases, we can see some spin waves. No much change by this kind of reversing the magnetization. Then once we have that, we can just simply, get the Fourier transform of the 2D plot, and with that we can define the wavelength that in this case is around 3 microns. This is very different to what we say, for example, we are in the perpendicular case. So this is what are the Demon-Ashbach spin waves. And you can clearly see this non-reciprocal effect that is very well known in the magnon community, but somehow this is, I guess, a beautiful example while doing this imaging. You can clearly see that in that position we have a stronger signal than in this other one. And of course, the wavelength is larger, around 20 microns. So we can do this for all the magnetic fields, and well, we can get this kind of a peanut way of controlling the wavelength, and indeed we can just tune it by rather a factor 6. Well, that was kind of the interest of showing this kind of imaging of the spin waves. But there's another thing that we can do, is just we can control the strength of the magnetic field that we are having, and we're going to be just comparing these two cases. First of all, the magnetization, that this is just applied parallel to the straight line. Well, you can see that, well, we have some changes, but really not much is going on, right? So it's just pretty much the same wavelength. However, we can just go now to the perpendicular case. And now you can clearly see that while we are decreasing the field, we are getting this kind of larger wavelength. So somehow, if we're coming again to this simile of the beach, if you like to make surfing, this is the way that you can get the waves. So this is the surfing area. This is just the 1D averages, so you can clearly see here we have something that is dispersive. Here we have something that is non-dispersive. Again, you can check it if we get the Fourier transform. Here, I mean, not much things going on. Here we have a dispersion, and somehow this is just how we can really, again, tune the wavelength in this case. However, here in this Demon Edgebrook scenario, this wavelength is pretty much constant. Well, you may have noticed still in one interesting detail, and is that here we have kind of nothing, right? So we can take into account this powerful technique that we can have this kind of a quantum sensor, so we can not only measure the, let's say, the contrast, but as well we can measure the position of the ESR, right? So we can measure the magnetic field that we're going to be having. So now let's just make here an ESR, and that's what we see. So we see just a single dip around 2.87. Now we can make a line. So we're going to be taking different ESR positions, and that's what you can see. So on top of the strip line, we have a broadened peak. That's normal, right? Because we have much more power. But then it's just like a pretty single line at 2.87 gigahertz. From that, you can get the autoplane magnetic field, and clearly you see nothing is getting. So the B set component is just simply 0. Now we can do the same, but here, to see what is going on. And that's what we see. So clearly in the edge, we have an out-of-plane component of the magnetic field that makes that these ESR dips, are detuned. So then if we're measuring at 2.87, we don't measure anything, but simply because our MB is not resonant with the driving that we are having, because since we have an out-of-plane magnetic field, we have Thinman splitting, and we have two dips. We can, again, do the line, and what we can see is just on top of the strip line, pretty much the same behavior, a broad peak. But now when we enter into the beach, we can see here this kind of shark coming from the ocean. So we have an out-of-plane component of the field that then is just, as we go in, it just becomes resonant to around 2.87, and then we don't have this kind of out-of-plane magnetic field. Well, so somehow this you can try to model, and then you can see we are going to be having a kind of a curling of the magnetization next to the film edge. Because somehow you can clearly see that if we have this kind of a scenario, we're applying a magnetic field pointing to the right, we're going to have some kind of competition, right? We have the magnetization, but as well we have shape anisotropies. We have intrinsic anisotropies that are very well known for permaloin, and this is going to be giving this kind of competition on the way of propagating these spin waves. And this just brings a natural question, right? So we have two ways to come to this situation. So for example, we can first of all, be rotating from that situation. So from this Demon-Edgebrook pointing down, we can rotate the magnetic field and be pointing to the right. So now counterclockwise situation. We can do the same thing, but no, in a clockwise situation. I will not just tell you what is going to be the difference. I just will show it, and that's what we're seeing. So we go counterclockwise, we have this situation that we saw before. So we have like nothing, and then some kind of waves. But if we now rotate in a clockwise way, we can clearly see here a very sharp contrast region on our contrast maps. We can do the same trick as we did, because we have our quantum sensor that we are very sensitive to out-of-plane magnetic field. So we're going to be making ESR traces along this line. And that's what we're going to be seeing. So here we saw this kind of a sharp shape. So we have an out-of-plane component of the magnetization. However, here in this bottom case, what we are going to be having is kind of a braided structure, and indeed this is the point where it was coming together, where we saw this kind of very sharp red line. We can do this for several lines, and then we're going to get a map of the field profile. So here we see that it's pretty much homogeneous. Here we only have this kind of a maximum, and then it goes together to 2.87, and here we have several lobes. And the way that we can try to do is just try to simulate it. In this case was thanks to the collaboration by Jaroslav Lanter and Artem Bondarenko. And then indeed what we can clearly see is that here we're having a spin reorientation. So this is kind of a Carlin state. Whereas here what we're having is a nucleation of a magnetic domain. So indeed it's predicted to be an L-type. And somehow we can really, with this kind of a very easy trick, try to see how the spin waves are, for example, in this case, interacting with a domain wall. But now we hear in this community about vortices, Hophions, skyrmions. So somehow you could play the same tricks and see how these topological properties are interacting, for example, with the spin waves. Yes, thinking, dreaming about the future. And somehow that's the kind of experiments I would have liked to share with you. Now I'll be coming to the conclusions, just saying that indeed for having this kind of behavior, we really need to emphasize the role of the anisotropy axis that we're going to be having in these materials for giving this kind of two different scenarios. So somehow if another way of tuning spin waves is just by doing anisotropy engineering. If you can grow films where you can control the anisotropy, you will be able to really control the spin wave dispersion. Well, so somehow I think I've convinced you, or at least that we can make these maps of the spin waves using MB magnetometry, so single spins in diamond. We can generate the spin waves. We can control them, in this case in a very easy way with an autoplane magnetic, with an in-plane magnetic field, and then we can sense them with the MB center. This can give rise to somehow conflict situations next to the edges where the magnetization is not well defined. If we're thinking in terms of magnetic devices, this is very important, right? Because you are doing everything smaller, and smaller means that you are going to be having edges where maybe the things are not behaving as you may be expecting. And in this context, well, MB magnetometry can be a really useful technique for trying to study them. And with that, just thank you very much for your attention.